Welcome to our discussion on trigonometric functions of angles. We're going to expand out from looking at trig functions on the unit circle and generalize them to any angle, any size circle. Just to remind ourselves that we can deal with angles both as radians or degrees. We tend to prefer radians, so whenever you're given your angle in degrees, it's usually easiest to convert to radians, but it's not necessary if you're going to use a calculator. If we wanted to find the trigonometric function values of 90 degrees, we would convert them to pi over 2 and then go back to our unit circle and remind ourselves pi over 2 is up at the top, sines equal to 1, cosines equal to 0, tangents undefined, and the rest fall in line from there. Now, these are those kind of specialty angles that we see all the time that I have mentioned before. Pi over 6, pi over 4, pi over 3, right? Pi over 2, etc., etc., etc. And of course 0. You obviously would be better served if you had all of these memorized. It's going to save you some time, but it's not at all necessary. That's way too much stuff to memorize. But if you just take a look at this table in general, you'll notice there's a lot of similarities. You see how you get these square root of 3's all over the place and the square root of 2's all over the place and 1's and 0's and undefineds, right? So it just helps you to realize that a lot of these things are similar. You get a lot of the same results in different places with different angles or with the same angle with a different trig function. So it's not like you have to memorize 500 things. You really only have to memorize a few. Back to our unit circle learning guide, if you want to call it. And as I've mentioned before, it's really all about memorizing this quadrant here. You really only care about the first quadrant. And if you can memorize these values, then it's going to help you figure out the rest, because they're all the same, just with different signs, right? Pluses and minuses. And these are cosine and sine, and everything else is built off of that. Okay, what if we want to try and find some trig function values of an angle? Well, first we have to remind ourselves that an angle doesn't have to be on the unit circle, right? I mean, the same angle on a unit circle can also be out further, where we have some distance r that's not necessarily a distance of 1, but the angle is still the same. And the triangles that are created by that angle are similar. If you remember what similar triangles are, we know that the ratio of this distance to this distance has to be the same as the ratio of the smaller one to the smaller one. So if we know something about the ratio on the unit circle, we know something about the ratio on any circle, right? Any radius r. And it basically comes down to this. Instead of sine equaling y, which is really, from this function, y over the radius, right? 1 over 1. We now know that this distance is just y over r. Right? So our vertical distance for sine is just this over the entire length. So now instead of just x, or instead of just y, it's y over r, where r is our radius, x over r, again, where r is our radius. This is still the same. It's still y over x, because if you do the algebra, remember this is sine over cosine, and if you write sine over cosine, you get y over r over x over r, and of course you flip and multiply, which gives you y over r times r over x. The r's cancel, and there's your y over x. Cosecant, right? 1 over sine, so you just flip it. 1 over cosine, you flip it. 1 over tangent, you flip it. You maybe remember SOHCAHTOA. SOHCAHTOA, stands for sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, and tangent equals opposite over adjacent. And if you think about your angle, right, and if this is my angle, this value out here is opposite, this value here is adjacent, and of course this is my hypotenuse. So when we say sine is opposite over hypotenuse, it's the y distance, right, that's my opposite, over the hypotenuse, which is r, y over r. And then cosine, which is my x distance over the radius, well, that's just my adjacent over hypotenuse. So SOHCAHTOA is really just this stuff in another way of memorizing it. All right, what if we want to try and find some trig function values? If we have this point -1, 3, we know there has to be some big circle, right? Some big circle out here. That's a horrible circle, but you get the idea. And this is its radius. And we can find these measurements are sine is the vertical, right? And cosine is the horizontal. We can find those distances based on this point. We know that our radius is always the square root of x squared plus y squared, because that comes from just the standard function of a circle centered at the origin, and then solving for r means taking the square root. We plug in the points that we know, right? These points have to be on this circle, so they have to satisfy this equation. So you plug in -1 and 3 for the points, and you get that r is the square root of 10. So this distance here, my r, is square root of 10. Now that I know r, and I was given x and y, right? I was given y equals 3. I now know r is square root of 10, and x was given as -1. I can plug all those bits and pieces into the formulas and very simply solve for sine, cosine, tangent, etc., etc., etc. You wouldn't even bother with any of these. As soon as you have sine and cosine, you have all the rest, right? Tangent is just their ratio, that over that. And you can see when you do that over that, these pieces cancel. You get the 3 over the -1, and there's your -3. And then this is 1 over this one, right? This is 1 over that one, and this is 1 over that one. All right, how about if we want to approximate trig values, right? These were precise answers. What if we want to approximate them using a calculator? Well, that's pretty simple. You just have to worry about what mode you're in, because if you're given A, which is in degrees, you got to make sure you're in the degree mode. And if you don't know what mode you're in, or you don't know what how to change it on your calculator, for the graphing calculators, it's very simple. It's this button right here that says mode, duh, and then radian versus degree. So you'd go down here and you'd choose degree, right, and then quit out of that. And now you want to do sine of 71. Well, there's your sine button, 71, enter, there's your answer. Okay. What if we wanted to do tangent of 5 pi over 7? We would have to change the mode back to radians. And now we can do tangent 5 times pi divided by 7. And there's the tangent answer. If we have this type of calculator, or any other simpler kind of scientific calculator, there's usually either a mode button, or in this case, a degree button. It says DRG for degree. I'll circle it in red. If you press that button, along the top of the screen will be your 3 choices. It'll be degree, radian, and I can't remember the third one, but obviously choose degree or radian using the arrow buttons. Here's the example written out, right? If you try these, this is the example. This is the answer we got before. If we wanted to do it again, we'd have to go back to radians to try the third one. How about determine the signs of the trig functions in each quadrant? Well, again, it's a good thing if you have these things memorized. It will save you some time. But if you just remember that cosine is the x, right? Cosine is left and right, and sine is your y. Sine is up and down, and then knowing that tangent is sine over cosine, and all the others, cotangent, cosecant, secant. If you have all those memorized as far as how they refer to cosine and sine, then you've got all this. You don't need to memorize it. You can always figure it out. Because if we're over here in this quadrant, you go, okay, well, if I'm over here, x is negative, right? And y is positive, because I'm left on my x, but I'm still up in the y direction. And so since y is based on, or so sine is based on y, sine is positive. And since cosecant is 1 over sine, it's also positive. Now, cosine is obviously negative, and since cosine is negative but sine is positive, we get tangent is negative. And then since cosine is negative, secant is negative, and because tangent's negative, cotangent's negative, and that's why all the others are negative. Okay? So you don't have to memorize this stuff. It's just built on sine and cosine. How about determining the quadrant that something is in, right? What quadrant is a certain angle in? Well, if we're told tangent is positive and cosine is negative, well, we know cosine is negative over here on this half, right? So either this quadrant or this quadrant is where cosine is negative. In this quadrant, sine is positive, which would make tangent negative, but down here, since cosine is negative and sine is negative, tangent is positive, we've got to be in this quadrant here. If we're given that tangent equals 3/2 and cosine is negative, we can find the exact values of sine and secant. Since tangent equals y over x, we can plug the values of -3 and -2 in, right? That's where our 3/2 come in. We know they're negative because they told us cosine was negative, so this value had to be negative, and since the whole fraction was positive, this also had to be negative. It really doesn't matter because when we plug it in here and square them, they become positive anyhow, and we get our radius is 13. Now that we have a radius of 13, we know that x and y are both negative. We can plug it back into our y over r, our x over r, and all the other formulas for all the other trig functions. How about if we're trying to find a reference angle? Well, first of all, what the heck is a reference angle? Here's a lot of words that are probably just going to confuse the heck out of you. So let's look at a picture instead. A reference angle is just the angle that is created between the line and the x-axis. So if this is my line here, then that's my reference angle. It's the angle that actually created that line. But remember, we always create our angles and our lines by starting at 0 and going counterclockwise. So in this example, theta is going all the way around to there. But we don't want to use that. We want to use the shorter, simpler version, so we use the rest of the piece that connects that down to here. So if this angle here, if theta was, let's say, 150 degrees, then the leftover bit would just be 180 minus it, and that would be a 30-degree reference angle. If we're down in the third quadrant, the same idea applies. Instead of going all the way around, let's just figure out how long this distance is. Because if we know how long this distance is, we can figure out everything we need to know about this triangle, and then we're going to have the same triangle over here as our reference triangle. It's really what we're doing when we talk about a reference angle. Same thing here if we're over in the fourth quadrant, it's just whatever's left, right? So you're just finding the distance between your line and the x-axis. Okay, here are some examples. If theta is 250, I always like to draw myself a picture and go, all right, if I'm at 250, I know this is 90, 180, 270. So 250 is somewhere in this quadrant. So if I want to find my reference angle, I know I'm looking for this distance, which is going to be 250 minus the 180 is going to give me that leftover bit, and there's my answer of 70. Same thing with 3 pi over 5. I got to figure out what that is. 3/5 pi. Well, I know this is 1/2, right? Or 2.5 fifths. So 3/5 is past it, and it's less than 1 full pi. So now I'm somewhere in this quadrant, and if 3/5 gets me to here, I got to figure out what the rest of it is. So it's going to be all the way around, which is pi minus this 3/5 will give me the leftover piece, and there's my 2/5 pi. The next example they give us, 3 pi over 2 we know is as a number is roughly 4.7, and 2 pi is roughly 6.28. So when they ask us to find the reference angle for 5.75, we got to figure out what that is in radians, and we know it's somewhere between 3/2 pi and 2. Again, draw a picture, right? 3/2 pi is all the way to there, right? And then 2 is coming all the way back to here. So we know we're somewhere in this quadrant. So to find this leftover piece here, we just do 2 minus our angle, right? Our angle is in red. Our angle takes us all the way around to here. So we take 2 minus the red bit, and that gives us the leftover. So there's my 2 pi minus 5.75, and we get that as my angle. And if we wanted to put it into radians, then we could convert it, but that is in radians, right? It's something in terms of pi that's actually written out as a decimal. You know, just like pi is 3.14, blah, 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 blah. That's a portion of pi. Okay, coterminal angles, a big fancy word for basically saying if you have something that's bigger than 360 degrees or 2 pi, i.e. if you've gone around the circle more than once, rather than talking about that angle in terms of its total spinning around and around and around and then stopping, well, it doesn't matter if you go around 47 times or just to this point and stop, the point on that line is still going to be in the same place. So rather than dealing with the big angle measurement, we can just deal with what's called the coterminal, the shorter version, right? The angle that's between 0 and 360 or 0 and 2 pi, depending on if you're talking about degrees or radians. So that's all we're doing, is we're finding it's kind of a reference angle for something that's bigger than a full revolution. The procedure for finding that reference angle is very simple. If the angle is bigger than 360 or 2 pi, then we first find the coterminal, i.e. take away all the revolutions and then see what's left, and then we proceed to step 2, which is the normal steps for finding this reference angle that we've done before. So for finding reference angles for things above 360 is the same as finding reference angles for a normal angle. You're getting rid of all the extraneous revolutions and just going to the other coterminal thing. Here's an example for trying to find sine of 1320. Well, take away all the 360s. Right? How many 360s can you take out of that? Well, you just, okay, 360, another one 720, another one 1080. The next one would be too much, so we can take 3 of them away, right? And we're left over with 240 degrees. So a 240 degree angle is the same thing as 1320. Instead of going 360, 720, 1080, and then keep going around to about here, we could instead just do this. Yoink! And we're in the same place. So that's all we're doing. We just found this 240 equivalent to getting us that same point. And now we can figure out sine of 240. And again, we don't want to do 240. We want to do its reference angle, which is this piece here in blue. So 240 minus the 180 piece gives us the leftover bit, which is 60. And now, if we have our unit circle memorized, we know sine of 60 is 3 pi over 2 when we're in quadrant 1, right? So over here we know it's 3 pi over 2, but because we're down here, the sine measurement is now going to be negative, and our answer is negative 3 pi over 2. So there's all of that kind of memorization tricks all rolled up into one. Another example, if we're trying to find tangent of negative 390, well, we can take the 360 off of it and be left with 30, and then know what 30 is as reference angle and go from there. For 59 pi over 6, we got to take all the 2 pi's out, right? 59 divided by 6 is just a little bit less than 60 divided by 6, which is 10. So it's a little bit smaller than 10 pi. So take 8 pi away and then see what's left over. Ends up being the 11 pi over 6. 11 pi over 6 is almost all the way around to 2 pi. So we know if we're trying to find our reference angle, right, 11 pi over 6 is going to be all the way around to here, because 12 pi over 6 gets you back to 2 pi. So we're looking for this reference angle, which is the last 1/6 pi that's left. So we just have to do whatever we're looking for as pi over 6. So secant of pi over 6 gives us this answer. Since we're down there in that fourth quadrant, secant, remember, was 1 over cosine, so it's positive. The reference angle was also positive, so we don't have to change signs, and the answer we get is the answer we're looking for. All right, one example of applying all of this. A golf ball is hit on a level fairway with an initial velocity of 128 feet per second and an initial angle of flight of 30 degrees. So if you want to visualize that, here's the ground, right? It's hit at an angle of 30 degrees. Okay? We can model the height of the ball. So at any given time, the height of the ball can be modeled by this simple trig equation, where v naught, right, v sub 0 is called v naught, is the initial velocity of 128 feet per second, and then theta is the initial angle of trajectory, in this case 30 degrees, and then negative 16t squared, that's just based on gravity. Okay, plug in everything we know. The height is going to be 128, because that's our v naught, t times sine of 30 minus 16t. We've got to deal with these things as radians, so we replace sine 30 with a radian degree, or since we already know some of our memorized things and we know that sine of 30 is just a half, we can go straight to just plugging in a half for sine 30, which gets us 64t, right? 128 times a half times t minus 16t squared. That factors out to that. And now the graph of that equation is a parabola. And we know that the maximum height of the ball, i.e. the maximum value of our function, is going to be the vertex of our parabola. So all we have to do is find that vertex. So, back to it written in standard form, 64t minus 16 squared. Right, we've got the height function is negative t squared plus 64t, right? Sorry, negative 16t squared, negative 16t squared plus 64t. So my A is negative 16, my B is 64, and just for continuity's sake, my C is 0. Minus B over 2A, right, gives me 2. Plug 2 back into the function, gives me 64. There's my vertex of 264. I know that it reaches a maximum height of 64 feet after 2 seconds, and then it starts to fall back to the earth. We can also set this function equal to 0, it's easier to look at it this way. If we set this function equal to 0, we know that the height is equal to 0 whenever each of the factors are equal to 0. So it's going to be 0 at time equals 0, duh, when it's first hit, and then also at 4. That's where they got this 4 seconds. We know that the height of 4 is going to equal 0, so that's when the height comes back down to nothing. Because the second part they asked us was to find the actual distance it traveled. Well, we found that it hits the ground after 4 seconds. So now we just have to find the distance it traveled after 4 seconds. And no, this is not a typo. It's not that all of a sudden we went to cosine instead of sine. Remember, the first function modeled height, and height is an up and down. That's a y, right? So therefore, that's a sine function. Now we're doing distance. Distance is a left and right thing. That's a cosine. So that's why we have a cosine function. We still have v naught, right, initial velocity. We still have time t. We still have cosine as being the initial angle. We can plug everything in. 4, right? What's our distance after 4 seconds, i.e. how far has it traveled when it hits the ground? With an initial velocity of 128 and an angle of 30, cosine of 30 is square root of 3 over 2. Plug all this stuff in, and we get roughly 443 feet, and we can basically join the PGA Tour because nobody hits a ball that far, unless you're just a superhuman gorilla. Okay, lastly, we can use some basic trig identities to help solve some things. These are some things that you want to kind of memorize. I know it's more junk to memorize, but really the number one thing to help you with stuff is to memorize this one, and then everything else is based on that, right? You know that tangent is sine over cosine, and then cotangent is the opposite. You know that cosecant's 1 over sine, secant's 1 over cosine. So those are all, you got it. If you have this one memorized as Pythagoras, right? Because remember, cosine is your x value. So this is really just x squared plus y squared equals r squared, where r is 1, right? So there's your trig identity. And then these just come from this first one. If we divide everything through by cosine squared, well, cosine squared over cosine squared is just 1. Sine over cosine is tangent, so sine squared over cosine squared is tangent squared. And then 1 over cosine is secant, so 1 over cosine squared is secant squared. And that's where this one comes from. If instead you divide everything through by sine squared, well, the sine squareds become 1, right? The cosine over sine squared, right? Cosine squared over sine squared is cotangent squared, and then 1 over sine squared gets you cosecant squared. So this one just comes from dividing everything by sine squared. If we're given sine t equals 1/3 and cosine t is negative, can we find cosine and tangent? Well, using Pythagorean identities, we know that sine squared plus cosine squared equals 1. We plug in the sine part as being 1/3. Now we've got cosine squared equals 1 minus a ninth, which means cosine squared equals 8/9. We can now take the square root of both sides, remembering that algebraically when we take a square root we have plus and minus. But because they told us that cosine was negative, right, then we know we have to use the negative version. Now that we know what sine is, 1/3, we were given that, and cosine is this, we just solved for, we can put those in our sine over cosine identity, which will tell us what tangent is, and we get tangent. Lastly, if we're given secant equals -2 and tangent is greater than 0, we can find what tangent is because of our other trig identity. We plug in the -2 for secant. We get tangent squared equals 3. We take the square root, plus and minus, but they told us tangent was greater than 0. So we now know tangent has to be the positive square root of 3. And that's it, guys. That's everything you need to know about basic trig identities and working with angles and trig functions.